Well, hello, ladies and gentlemen. We're going to move on from chapter 5, which is the second law of thermodynamics. And we're going to move on to concretizing the second law in the most thoroughly rigorous and mathematical way possible, so that we can start using the second law automatically and in a mathematically rigorous way to solve problems. Remember all those pictures that we had, the Clausius inequality, the Kelvin-Planck statement of the second, the Clausius statement, the Kelvin-Planck statement of the second law. Those pictures are gone. We have the Clausius inequality, which we derived last time. It's an inequality, which is a bit of a pain, but it's still a mathematical representation of the second law. But we're going to improve on that today. We're going to improve on the Clausius inequality by deriving, or at least justifying, the existence of a new property, entropy, symbolized by the letter S. So we're going to move on to entropy today. In particular, we're going to develop the closed system entropy balance, do a little derivation today, derive the entropy balance for our property S, or entropy. This entropy balance is going to be a little bit strange looking, stranger than the energy balance, less intuitive. So we're going to spend a little bit of time talking about how to interpret each term in the entropy balance. We'll then move on to various versions of the entropy balance for a closed system. The overall process, rate-based, differential or infinitesimal process, just like for the energy balance. The entropy balance has different versions which are more or less helpful to solve certain kinds of problems. Then we're going to look at how to interpret this new term. I told you the entropy balance is going to look a little bit strange. It's going to look strange. One of the reasons it's going to look strange is because you have this entropy source term. Entropy can be generated due to irreversibilities within the system. Remember the second law about reversible versus irreversible processes? Well, the presence of irreversibilities within the system during the process results in entropy S being generated. Entropy is not conserved like energy. It can be generated. So we have this S-gen term. S-gen or S-generated, which we'll investigate. How is S generated? Where is it generated? We'll talk about that when the time comes. And then we'll try to make concretize the entropy balance for a closed system by doing a very simple problem to get you started. We'll do heat transfer from hot to cold through a wall. So we have a plain wall. Heat flows from left to right, from the hot side to the cold side of the wall. We're going to do an entropy balance on the inside of the wall. We'll talk about how to interpret the results, okay? Okay, so let's get started here. Let's get started. What's this thing entropy about? Well, the first thing I'm going to do is I'm going to write the Clausius inequality. I'm going to write the Clausius inequality right here. So recall, over a cycle, the differential amount of heat transfer divided by the temperature at which the heat transfer occurs has got to be equal to the following. If the cycle is reversible, the cyclic integral is 0. Reversible cycle. So that integral is 0 when it's a reversible cycle composed of reversible processes. And it is less than 0 when there are irreversible processes within the cycle, or irreversibilities. So that cyclic integral can take on two values, either 0 or something negative, depending on the process. All right? Now, let's look at a system. Let's look at a system that moves from state 1 to state 2 and back to state one. So it undergoes a cycle. Undergoes a cycle. All right? Let me show you what the cycle might look like. So here's state one. Here's state two. And we're back to state one again. Okay? Now I'm going to put a hard constraint and a soft constraint on this cycle. A hard constraint is process 2 to 3 is going to be reversible. That's going to be my hard constraint. 2 to 1, did I say 2 to 3? 2 to 1, reversible. 2 to 1 is reversible. I'm going to put that constraint on my process. And I'm going to put a soft constraint, which means in a moment I'm going to relax it. I'm going to say 1 to 2 is also reversible. So I'm just going to write reversible right next to process 1 to 2. Okay? So this is a hard constraint from 2 to 1. So I'm going to put some explanation points here. And 1 to 2 for the moment is reversible. Okay? So let's write the Clausius inequality here. Okay? Now I'm going to break up this inequality, the Clausius integral. Sorry, I'm going to write the Clausius integral. Let's break it up into process 1 to 2 and 2 to 1. So this is the integral of del Q over T from 1 to 2. Plus the integral of del Q over T to back to 1. All right? Now this, I'm going to say that this path here, 2 to 1, is not only reversible, but the path is fixed and reversible. I'm going to put some blue chalk here. So not only is it reversible, but it is a fixed path. So I'm going to write here 2 to 1 reversible, and then I'm also going to write fixed. Good. Explanation points right there, fixed. So if 2 back to 1 is fixed, that means this integral right here, 2 to 1 is fixed. Why? Because the path 2 to 1 is fixed. So this guy is fixed. All right, the second integral is fixed. Now, I've also said for the moment that both of these processes are reversible. So I'm going to put brackets around the del Q over T. And I'm going to write reversible, R-E-V, reversible, reversible, indicating that those are evaluated over a reversible process, all right? Okay, so if these are both reversible processes and the cycle is reversible, then the Clausius inequality says that this cyclic integral must be equal to 0. Okay? So that implies I'm going to take the del Q over T from state 1 to state 2 over on the other side of the equation. I'm going to flip the whole equation. So this implies that the integral from state 1 to state 2 of del Q over T, and remember process 1 to 2 for right now is reversible. Reversible, R-E-V, is equal to minus the integral of del Q over T, and this is also reversible process, from state 2 to 1. And remember, this is fixed. Why? Because process 2 to 1 is a fixed process, and it's reversible. Okay, let's think about this for a minute. Let's say I vary process 1 to 2. 2 to 1 is fixed, but 1 to 2 is not necessarily fixed. I can go from state 1 to state 2 along any path I want. Let's say I go along a new path. Okay, a new path. Oops, gotta come back. There we go. Which is also a reversible path. So let's say both of these are reversible. So I can vary the path here. Vary path. So the left integral is evaluated over a variable path that can change. And the right side integral is fixed because I've fixed the path. What this is saying is this integral, del Q over T from state 1 to state 2, is invariant. It has the same value for any path required or provided that path is reversible. This is fixed, so that means this is fixed. This integral has the same value no matter what the path is. No matter what the path is, it has the same value provided that path is reversible. So this strongly suggests that there exists some kind of property or point function. Property or point function called S, of which the change is equal to this integral over a reversible path. This is path independent. It basically means that this thing represents the change in a property. Okay? So let me write what I have here. I'm going to write it over here in the corner, and we're going to play with it. So let me write down, oops. Let me write down what I have written over on the other side. We're going to play with it. Let's take what's important and see where it takes us. So I've hypothesized a new property, S. S equals entropy of which delta S from 1 to 2 is equal to the integral of del Q over T for a reversible, or I'll just put REV, for a reversible process. Delta S from 1 to 2 is equal to del Q over T for a reversible process. That's what we concluded by having a fixed and then a variable path and evaluating the cyclic integral del Q over T over the cycle. And we utilize, of course, the Clausius inequality, which says that that cyclic integral is 0 if it's a reversible cycle. All right? Okay, let me draw our system path one more time. Okay, so I have 1, 2, back to 1. And I've said here that the process 2 to 1 is reversible and fixed. That's our blue one, as I recall, blue and white. Okay. And remember, 1 to 2 can take various paths, all right? But 2 to 1 is fixed. 2 to 1 is fixed. Okay? Now, let's play with this just a little bit more. Let me write my cyclic integral again, my Clausius inequality. So remember, del Q over T is equal to 0 for a reversible process and less than 0 for an irreversible process or cycle. Okay, so let's write the Clausius inequality one more time. Let's play the same game we did just a moment ago, but I'm going to let 1 to 2 be irreversible. I don't care what path it is, provided it's an irreversible path. So I'm just going to write here, irreversible. Let's just say these path 1 to 2, whatever that path is, now it's irreversible. Let's give that a shot. So let's write out the cyclic integral. Integral del Q over T. Again, that's going to be equal to the cyclic integral of del Q over T from 1 to 2 plus the cyclic integral of del Q over T. And remember, 2 to 1 is reversible. REV, reversible. 1 to 2, 2 to 1. Now, we've already hypothesized that del Q over T for a reversible process is equal to a change in a property, delta S. Now, this here is the integral of del Q over T from 2 to 1. So that means that this integral here is actually delta S from 2 to 1. Delta S from 2 to 1. Okay? All right? Now, because there are some irreversibilities in the cycle, the Clausius inequality says that the cyclic integral del Q over T over the cycle has got to be less than 0. Less than 0 because there are irreversibilities present in this process. Any path from 1 to 2, I'm telling you, is now irreversible. Okay? Now, I'm going to take delta S 2 to 1 and put it over on the other side of the inequality. So I get del Q over T integral from 1 to 2 is less than negative delta S from 2 to 1. The negative sign is because I'm taking it over on the other side of the equation, all right? Now this delta S from 2 to 1 is actually negative delta S from 2 to 1 is negative S1 minus S2. That's what delta S2 to 1 means, okay? If I distribute the negative sign, I get S2 minus S1, which is equal to delta S1 to 2. So this quantity here is actually equal to delta S1 to 2. Okay? Now I'm going to flip the equation and put the delta S change in entropy from state 1 to state 2. I'm going to put it on the other side of the inequality. I'm going to flip the whole inequality. Delta S 1 to 2 is greater than the integral of del Q over T 1 to 2. All right? And remember, this is for an irreversible process. That's for an irreversible process. Now let's look at what we just developed a moment ago. For a reversible process, delta S from 1 to 2 is equal to del Q over T for a reversible process. So let me write this equation right below what we've just developed. So we also have delta S from 1 to 2 is equal to the integral of del Q over T 1 to 2, provided 1 to 2 is a reversible process. So this quantity, delta S, is greater than this integral if it's an irreversible process and equal to the integral for a, greater than del Q integral of del Q over T for an irreversible process and equal to del Q over T integral of for a reversible process. This is what I'm going to do. I'm going to take this fact and I'm going to write out a new conservation equation for S. A brand new conservation or entropy balance for S. Delta S from 1 to 2 is equal to integral del Q over T plus S gen. Now, what is this S gen about? S gen, or S generated, is equal to 0 if the process is reversible, process 1 to 2, and greater than 0 for an irreversible process 1 to 2. What has happened here? What's this S gen about? Well, I've kind of tricked you a little bit. Let's go back to what we did here. Let's focus on these two equations right here. Basically, it says delta S from 1 to 2 is either equal to or greater than this integral depending on the process. And that's shown by this inequality right here, okay? The equality and the inequality. I've gotten rid of the inequality by swallowing it up into a brand new term called S gen. I've gotten rid of this inequality here. We don't want to work with inequalities. We want to work with equalities. That's what we're used to in mathematics and physics and engineering. So I got rid of the inequality. See here, delta S is equal to the integral of del Q over T plus S gen. I got rid of the inequality by swallowing it up into this S generated term, where S generated is 0 if it's a reversible process and positive if it is a, 0 if it's a reversible process and positive if it is a irreversible process. Okay? So, let's take a pause here.